This is Lesson 3, Choose the Data, Exercise 3B, Choose a Coordinate System. When you choose a coordinate system, you're choosing one way, among many possible ways, to use measurements to describe the locations of places in your data. Like how many feet or meters away is place A or place B from a given reference point. You're also choosing one way, among many possible ways, to draw those places on a flat surface, instead of on a sphere, which is where they really belong. That part of a coordinate system is called a map projection. Drawing places on a flat surface distorts their spatial properties, so place A may look bigger than it really is, or the distance from A to B may be measured as 1,000 miles when in fact it's 950. You should choose a coordinate system that minimizes spatial distortion for the area you're studying. In this exercise, we have 3 objectives. First, we'll see how to find out the coordinate system of a dataset. Every dataset has one. Second, we'll see how to project data on the fly. This means temporarily forcing some layers in a map into a coordinate system that isn't their own. That will also give us a chance to look at spatial distortion. Third, we'll choose an appropriate coordinate system for our study area. We'll also assign that system permanently to our datasets in Lesson 4. Let's start ArcMap with a new map. In the Catalog window, navigate to Source Data and the Esri Geodatabase. Here's how to find the coordinate system of a dataset. Right-click a feature class like this one and choose Properties. Click the XY Coordinate System tab. You see its name, GCS WGS 1984. GCS stands for Geographic Coordinate System, which means this data is stored in latitude, longitude values, which means it doesn't have a projection. Close the dialog box. Now, add the data to the map. It draws flat on the screen because it has to, but don't use it in this condition. You can't do good analysis on it. Okay, here's another way to find out the coordinate system. Open the Layer Properties and click the Source tab. Scroll down. You can see the coordinate system here too, but not as many details. That completes our first objective. Close the Layer Properties. And notice the coordinate readout in the lower right corner. It tells you the coordinates of your current location as you move the cursor around the map. Okay, let's get warmed up for our next objective. From the View menu, choose Data Frame Properties. Click the Coordinate System tab. Notice the current system. Once again, it's GCS WGS 1984. When you add the first layer to a data frame, the data frame recognizes its coordinate system. That will be important in a minute. Close the data frame properties. Now click the Create Viewer Window tool. This lets you draw a new window on your data, which you can navigate independently of the main window. It's useful for seeing different places at the same time and stuff like that. But we have something else in mind. From the Insert menu, choose Data Frame. Now we have 2 data frames, which is like having 2 maps in the same map document. Only one is active at a time. Right now, it's the new one, which is empty, even though the viewer window is still showing the data from the inactive data frame. Open the data frame properties for the new data frame. The current coordinate system says no projection. That's because we haven't added a layer yet. Close the dialog box. Click the Add Data drop-down arrow. Add Basemap Imagery. Move the window out of the way and move the cursor around the map. In the coordinate readout, the units are meters, not degrees. That tells you that the data has a good rule for drawing in a flat space. Open the data frame properties again. Now the data frame recognizes the coordinate system of the base map, which has a long name, but the key word here is Mercator. Close the dialog box. What happens if we add another layer? In the first data frame, right-click State and choose Copy. Right-click the new data frame and paste the layer into it. Let's zoom in. Alaska and the other states are properly aligned with the base map imagery. That's what on-the-fly projection does. ArcMap is forcing the state layer to use the Mercator coordinate system so both layers line up, and that action is limited just to this data frame. Look at the features in the viewer window. They're a lot more stretched out. The shapes in the new data frame are correct. One thing about the Mercator projection is that it doesn't distort shapes. Close the viewer window and zoom in on Alaska. What the Mercator projection does distort is area, especially far away from the equator. Click the Measure tool. Clear any previous measurements. Click the button to measure a feature. Make sure the area units are miles. Now just click anywhere on Alaska, and you get a measurement value. It's over 3 million square miles, which is pretty far off. Open the Layer Attribute table and select Alaska. Scroll over to the square miles field. The true area, shown here, is about 580,000 square miles. The Mercator projection exaggerated the area by a factor of 5. Close the table and clear the selection. Open the data frame properties again. We can change the system the data frame recognizes. This will project both layers on the fly. We'll try a system designed specifically for Alaska that doesn't distort area. Click the predefined folder, which has all the coordinate systems ArcMap knows about. Expand Projected Coordinate Systems, Continental, North America, and click the first one, Alaska Albers Equal Area Conic. Click OK. Notice that Alaska is smaller now. It's not filling up the screen, even though the map scale is the same. Click on it again. This time, the area measurement is right. Using an appropriate coordinate system isn't just important for measurements, but for all kinds of analysis. Close the measure box. The shape of Alaska looks right. A coordinate system designed for a certain area minimizes all types of distortion for that area. Zoom to the full extent. You can see that a good system for Alaska comes at a price. The rest of the world is distorted. It can't even be completely shown. Okay, that's it for on-the-fly projection and distortion. The last thing we need to do is choose a coordinate system that's appropriate for Southern California. In the Catalog window, expand the City of LA folder and add LA River. Zoom to the layer. Turn off the state layer. Right-click the river symbol and make it blue. We should make it thicker too. So double-click to open the symbol selector and change the width. Open the data frame properties again. Expand the Layers folder. The Layers folder shows the coordinate system of all the layers and sublayers in the data frame. It's another way to find out, just like feature class properties and layer properties. Expand LA River. It uses the state plane system, which is actually a patchwork of systems covering the United States, with locally optimized zones within each state. California Zone 5 covers Los Angeles. Click on the system. That makes the data frame recognize it immediately. Click OK. And all the layers in the data frame are projected on the fly to the state plane California Zone 5. For small area mapping projects in the US, the state plane system is a standard, so that's what we'll use. Save the map document. Call it Lessons 3B. And exit ArcMap.